Alright, just gonna keep on trucking. That video was about 20 minutes and I felt like that's pretty good for that. So let's see. Video 2, we're gonna look at, looks like we're looking at contacts. Okay. Oh man, this one's kind of sideways. So the geologic symbol for lithologic and fault contacts. Lithologic is the contact showing dips, so this is basically like showing how much it's dipping, so it's dipping 60 degrees from horizontal. This is basically showing you what you'll see on geological maps, like the kind of symbology that you'll see and like what it means. The contact is an approximate location. If it's dashed, if it's like these more big blocky dashes, it's like contact is concealed, so we don't know. This one's like, I don't know, might be a fault there. The fault's there, but you can't really see it. That's probably where it is, and this is for sure where it's at. So, just take a gander at those, and if you see it on geological maps, that's what it is. Conformities. Unconformity is basically like a if there's explosion contacts of rocks with large age gaps, so like this is 1.6 billion years old, and then all this stuff up here gets eroded away, and then some deposition of sedimentary rock goes on top of it, and that right there is the unconformity. I got a little hand. So this is basically like just geology 101 kind of stuff. This is just like Miocene volcanics, Jurassic sediments, Precambrian granite, Paleozoic sediment. So this is the nonconformity, saying where it's a volcanic rock, like young sedimentary is on top of volcanic. Oh, they're over here. Okay, yeah. Okay, here, yeah. Nonconformity is young sedimentary and volcanic, the old igneous and metamorphic. So basically, young sedimentary on volcanic rocks. That's a nonconformity. Right here is an angular unconformity, which is basically just young material and old material that's bedding is layered. Disconformity is a young sedimentary on an older sedimentary. So nonconformity is when there's sedimentary rock on igneous, and disconformity is when there's young sedimentary rock on older sedimentary rock. There's basically just a big gap of age. Like if it's a few thousand years, it's like it's probably not really a disconformity or nonconformity. But if it's like a million years difference from the time that one sedimentary rock was put on another, then that's definitely a disconformity. It's basically just a big age gap. So disconformities are parallel to one another, where angular conformities are a flat layer over a slanted one. So it's basically just saying like, well, right here you have a sediment on top of a sediment. That could be considered a disconformity, but the sediment's angled, so it'd be like an angular disconformity. Kind of like, I guess, what you could call it. How defined contact beds above. Oh yeah, this is pretty cool. So like right here, this is basically a zoom in of like this angular unconformity, where this Paleozoic sediment and this Jurassic sediments are in contact, but you have some of the Paleozoic sediments kind of inside of there, like little pebbles and stuff. And that basically comes from like as rocks are deposited, like they'll kind of weather and scoop away the rock that's getting deposited on top of, and then you'll find like little inclusions inside of the newer rock layer. So intrusive contacts, magmatic. Oh, that's cool. Intrusive rocks are areas where magma has solidified after flowing into a country rock. A country rock is, oh, it's right here. Man, my notes are nice. So, country rock is a rock that hosts the inclusion or intrusion, and the country rock may be any type of rock, sediments, metamorphic, or igneous. So it's basically like the country rock is just the bigger layer, and if the intrusion is coming inside of it, man, I need like a whiteboard or something. So like it's basically the rock that's hosting the inclusion. You can kind of see like right here, this 1.3 billion year old rock is the country rock, and this 1.2 billion year inclusion or intrusion is the intrusion. So country rock intrusion. Apophysis. Apophysis. I don't remember how to say that word. That's a hard one. Apophysis. Tongue-like injections into country rock may occur near intrusive contact. So that's basically just like the forms of the edges of them. You know, like a lot of this stuff, like with structural geology, is like stuff that you'll see in the field, and it's like, oh, this is the apophysis, whatever. You know, like you'll know that is a characteristic of the inclusion, like being like tongued into the oh, I should probably do it to where you can see, tongued into the country rock, you know, and there'll be a few of them usually within one area. So xenoliths are a detached country rock. Detached country rock that became incorporated into the intrusion. So that's like, you know, like there's an intrusion coming into the country rock, and like because it's hot and because it's like a different like amount of pressure and amount of heat, and you know, like different kind of physical characteristics acting on this, like let's just say it's a sedimentary rock, it's gonna pull some of them into it. So that's like kind of the inclusions over here, where it's like this is the newer material and it's stealing from the material that was laid down before. Kind of the same principle here with the xenoliths, is that it's stealing the country rock away from it because it was the layer that was already there. Boudinage is, I think that's French for sausage, but I think so. So sausage-like globs that form due to extension in boudin necks forming dikes. So this is basically like how these form is like if there's a whole dike, right, and it goes through, and a dike is like a straight line of like basically intrusive material. So like let's say there's a long thin line of intrusive magmatics, right? Well, as the pressures push and move it, they'll form into like these little like kind of like oval kind of shapes like this, you know, depending on, you know, and they'll be oriented different ways, but those are the boudinages, and you'll see them in different areas. Like if there's other dikes around, like you'll probably see like a few boudinages. An enclave is pieces of igneous rock that solidify within the melt near chill zones that indicate magmatic flow. Oh, it's the flow direction is basically that probably should be direction that indicate magmatic flow. So this is basically like within the melt, like as a flow is going through, like if you imagine like a lava flow shifting through, pieces of it are gonna start cooling faster. Like the pieces that are more resistant to heat are going to kind of glump up together, you know, and cool faster. And then if it's like a cylinder and the flow's going this direction, it's going to kind of shift and then solidify with the direction of flow. So chill zones are areas where metamorphism may take place due to intrusions contacting sedimentary rocks. So like you know, if you have, you know, a bucket of hot water and you pour it outside, you know, you have a bowl of cold sand and you pour it on it, you know, the water is going to cool more readily because it's contacting something that's not as hot as itself. And that would be the chill zone, is like a little area of, you know, like where the heat is being dispersed. So contact metamorphism happens around the chill zones, and that's where something really hot hits something really cool, and then it melts it and changes its composition. So like limestone, the igneous rock hits the limestone, and this would be like the contact metamorphosed limestone that turns into marble, you know. So here's an example of an intrusion baking a limestone, metamorphizing it into marble. Yeah, so there's that. Fault and shear zone contacts. Okay, So usually indicated by fault and shear zone contacts. A fault surface is usually indicated by a fracture where two formations of rock continuously broken. Rock continuity is broken. So a fault surface is basically just the line in which that like something shifts or moves. That's the fault. Is the area in which rocks are moving in relation to each other. And the fault surface is indicated by a fracture where two formations of rock continuity is broken. So like if my hands were just one hand and they slipped, that is the fault, because the continuity of my one mega hand shifting into this two little hands is where the fault surface would be. The fault zones, basically just an entire zone, because like a fault usually won't just be like, oh, like in the books it's shown as like one line as a normal fault, but it's usually a little like an area. It's a general space in which things are shifted, and sometimes it is along just one line, but that's as you go deeper, that one line kind of spans out, and it's like all of this area is faulted, and now it's just right here, but it goes up in a little bit of this area. So that's basically saying that, when something shifts, there's other pieces that are going to break and shift along with it. Now we're getting to some fun stuff. Some fault zones may be finely polished into a slicked surface due to the differential movement. A slickened surface is almost always marked by striations or gouges that reflect fault movement. So right here, I guess it didn't draw it very well, but you can, like, this area is like kind of more bulbous, and then it pinches out into like a teardrop shape, and the tip of the teardrop is usually where it moves. It's basically like digging into something, and then as it lifts, it's less pressure. It's like and as it goes up off of my hand, then it's digging deep right here, and then not as deep up here. But the direction of movement because of stuff like that. Which, I guess a disclaimer would be like, just because you see that doesn't mean like that's the definite movement. When you're looking at a surface, you should take in a lot of the other information, all the other clues that you see to kind of piece together ideas. It's never just one thing like, oh, I saw this slickened surface and that guarantees that moves this direction. Sometimes that's good enough to get a general idea, but that's usually just one clue that you incorporate with other clues in an entire area to describe something that's going on. Yep, shear zone. Yep, shear zone's just the area in which that it was sheared, Like, you can see, like, this was a dike, and that it got shifted to this and shifted that way. Look at that. Moved over to the left. Alright, so... Wow, man, some of these just got really messed up. I'm probably not going to fix it, though. I'm just going to read off my notes. Oh, wow, man, I think I got, like, right to it. What? Sweet. Yeah, like this right here is like a solid blue thing in my notebook. Like, my notebook is so much better on my hands than it did in scans, but whatever. Primary structures is a structure that occurs as the rock is being formed, and before sediment is lithified, lava stops moving and becomes volcanic rock. Intruding magma solidifies into plutonic rock. So it's basically like the primary structure is like what happens before things start happening. Like if it's a flat surface, that's the primary structure, and then faults come. Well, the primary structure was just that one solid flat bed. The structures reflect conditions during formations. These structures reflect conditions during formation. Yeah, so the primary structures tell you what condition that the rocks were put in. Like if there's a lot of pillow basalts, then it's like, oh, well, that was probably laying with on the surface at some point. And I don't know, I do get into pillow basalts later. So yeah, primary structures, like, think about pillow basalts as primary structures whenever when thinking. We'll go forward. I'm not doing a very good job at describing that. but I think you'll be able to piece it together. Bedding, sedimentary, fundamental primary structures like the bedding for sedimentary and the flow layering for volcanic. So like the pillow basalts. Oh, actually, I'm getting that. Oh, yeah. This is it. This is how we see the formation as a whole, facing indicators. Oh, the facing indicators. So before a layer of rock gets like all broken up and all messed up and changed around, the primary structures tell you like which end was up, and that can help with like aging rocks or like deciding, you know, what happened in an area. So cross beds, and for some reason, man, that thing went super sideways. So cross beds has a sweeping shape in which the bottom of the formation and the bottom of the sweep are almost parallel, while the top is truncated. This occurs in both aqueous and aeolian environments. Aqueous is, has to do with water. Aeolian has to do with wind. So basically, that's just saying like, as sedimentary rock gets layered on top of one another, down here near the bottom, this would be the surface, and like this is where the sand is getting poured down a slope, right? So this is the baseline of it, which means that the up direction is up here, up towards the top of the page. The sand is going to get piled and piled and piled up here. So like that's important. Like if the bed was flipped all the way over upside down, then you know like, oh hey, here's the flat surfaces and there's the truncated, which means cut off, side. So this thing must have been flipped upside down, but this one is right side up. This one is upside down. So, graded bedding. So this is, I'll read it because it's cut off. So this is class or grain size becomes smaller by centimeters or meters towards the top of the layer. This occurs in places that are able to move the sediment. As the force moving sediment decreases, it is unable to carry large materials. As it slows, the larger particles set to the bottom first. They settle to the bottom first. So if you reach into like a driveway, like a dirt road, and you put a shovel in, you get a whole bunch of randomly assorted material, and then you put it in a big bucket. The big rocks are going to hit the bottom first, and then like little rocks and littler rocks until the dust particles start to settle. That's basically what graded bedding is. Oh, here we go. Oscillation ripple marks. Okay, so ripple marks are a really big indicator when trying to figure out which way is up, and luckily, yeah, this one totally scanned in a good way, so I can just not have to read my notes. So, oscillation ripple marks, that's basically like right here where they're like evenly spaced and they're kind of perfect little ripple marks, is saying that like the water movement was at a shallow marine and that it was sloshing back and forth. As sediment went down, it just kind of lithified in that shape. Or formed where waves come back and forth. Yep. And don't confuse them with current ripple marks. And the difference is, like, as you can see, like these are more like kind of like, they have a little slope up and then go down, slope up, go down, and that means that the flow is going that way. So just kind of like back here, you can tell that this is where the sand was going down. That's the slope, the down slope of it. That would be this right here, this little leg. So that's just showing you that the direction is that way, which means that the upward facing direction is again towards the north of my paper, which I think all of these will be. And pillow structures. So all of these ones that we just described in here were all sedimentary structures. I think that it goes to, pillow structures is an igneous one, where the pillows on top form and the ones that lie beneath the earth, beneath them, each with a rounded top. So this is basically like this area cooled and the lava kind of expanded and made this like kind of teardrop shape, and then this layer came in and filled where the spaces were missing, and then this third layer came in and filled, just so on and so forth, bottom to top. Extra. Mud cracks facing indicators. When mud cracks form, they may fill with sand, And these spaces taper downwards, so kind of like this, like into a V. So they may be used to find the top of the structure. Okay, so all of these primary structures are basically just different ways of figuring out which way is up. And it's just if you see a huge road cut and there's igneous rocks in there and there's sedimentary rocks and there's sandstones and there's mudstones and there's all this stuff and there's all this noise, then you have to be able to look through it and piece apart, like, okay, well, I see these pillow structures and it's facing that way is up, and then I see these flow structures and they're on top of the pillow structures, but they're also going up, so that direction must have been up. And same thing with like these cracks, like as a layer is, if this is the mud layer right here, then it's going to, if you've ever seen like a dried out cracked up surface, like the tops kind of going like this, and this is the bottom down here, down at the tips of my fingers would be the bottom of the mud cracks, the mud layers, and sand would fill in those spaces, preserving those mud cracks facing indicators. Oh, did I go too far? Oh no, that one's just okay. Cool. So here's some metamorphic structures. Deformation and metamorphism can occur in high temperature and stress environments. Rock cleavage. Low to moderate temperature is anything below 300 degrees Celsius with confining stress. So rocks break or cleave in a planar fashion. So what it means by planar fashion is that, like, if you think three-dimensionally, like the plane's like a cake, right? So this is the plane. We're looking at it from this plane, and we're looking at these individual planes. So the confining pressure squishes everything together, and basically, like, these are the individual planes. The pages represent the individual planes of a rock, and the confining pressure is in a different plane, and as it pushes, it interacts with all those planes simultaneously. And sometimes, like, they can react in different ways. They don't all have to shift up, like some of them can bulge out and stuff like that. Cleavage is perpendicular to sigma 1, the greatest force, and typically cuts across bedding. Stress being applied to rock shortens and develops a planar feature that the rocks might cleave from. So yeah, this would be sigma 1, and so cleavage would be probably like within this area right here, like just up and down. Foliation is a general term for any planar metamorphic fabric, but is commonly reserved for stronger metamorphosed rock and requires differential stress. So like there's a lot of like matrix, cleavage, foliation, like there's a lot of terms in geology that can be kind of ambiguous and kind of interchanged, and can just kind of be like general terms. Like foliation is one, and a good way to think about it is as an organization of geometry within a rock unit. So like these are all like different little minerals, and sigma 1 comes in and pushes them all down and then layers them, organizes them. So this would be the foliation. Types of foliation: schistosity, which is crystals of mica and other minerals, makes rocks shiny. So sigma 1 comes in, squishes these. The foliated crystals become kind of like, basically this is like a different kind of representation of the same thing. Foliation is usually parallel to flattened crystals. So like this would be the foliation, and same thing right here. Gneissic is dark and light colored bands that are organized during pressure. So, disorganized matrix of material gets squished, and then, like goes along with like. Ductile shearing can form foliation. So, lineation is linear formations in a rock unit. So, basically it's all lined up. All these things are, like this is lineation. It's all lined up.